letter for him to grad school, so David is responsible for the quality of this colloquium, and we know it's going to be excellent. Then afterwards he did his PhD at Stanford in the group of Aaron Kapitulnik. Then he moved in NIST in Boulder, and in 2011 he started his own group at the University of Nevada, Reno, and last year he moved to Northwestern. So, well, I would say from my own perspective that Andrew is pretty unique condensed matter experimentalist because he knows how to talk to high energy theorists. He knows how to teach high energy theory students. He taught last summer in Trieste at the school for high energy physics. And also he even knows how to write papers together with high energy theorists. And at the same time, very importantly, he knows how to keep them out of his lab, so he can get this job done. And we'll hear now what comes out of this.
So thanks, Sergey, for the introduction and for the invitation to visit. It's been great visiting today. And today I'm going to tell you about some of the work we're doing in our lab, where we're basically using AMO-based sensors to look at various fundamental physics experiments. Let's see, is there a laser maybe somewhere? Or
there's a
stick. Oh, okay, that's just as good.
It used to be here yesterday.
It's analog.
Well,
where is it? Someone stole it.
Check under the board there. I think it's hiding under that.
Or maybe it got carried to another room.
Well, I can manage without. It's not a big deal.
AMO means atomic.
Yes, atomic molecular optical.
Large, Matt, and buy a second.
Oh.
Actually, I think it's, I just got it at a hardware store.
It's fine. I can survive. So we're using AMO-based methods for looking at various kinds of fundamental physics problems. Normally, when we think of fundamental physics, what comes to mind for many of us are things like the Large Hadron Collider, where the idea is to push the energy frontier to smash particles together at higher energies that have never been looked at before. And of course, the LHC has been very successful in discovering the Higgs and is continuing to look for new physics beyond the standard model, in particular things like supersymmetry. But there's another frontier that one can think of that's not, not the so-called energy frontier, but rather the precision frontier, where the idea then is to not use large machines like this, but rather to do very high precision measurements to look for physics beyond the standard model. And so one example of such an experiment is would be to look for electric dipole moments of fundamental particles, for example, nucleons, electrons, or nuclei, neutrons. So the idea would be that by measuring and searching for these dipole moments, one can also look for high energy physics, for example, like supersymmetry. As another different example, there are precision experiments, for example, the Axion dark matter experiment, which is using a microwave cavity to look for a very low mass weakly interacting particle called the Axion, which could potentially create a photon in that cavity and then be detected. Where this experiment really is looking for such a weakly interacting and such a light particle that the collider is just not the right tool to think about using. Oh, perfect, thanks. The collider is really not the right tool to look for that kind of physics. So our lab is doing experiments more on this. In the second column here on the precision frontier, I wanted to mention, as Sergey already said, our lab recently moved from the University of Nevada in Reno to Northwestern University, where there is a newly established Center for Fundamental Physics, where the idea is to collect together a bunch of faculty doing these kind of experiments, where we do basically tabletop experiments to look for fundamental physics kind of questions. And so in addition to our efforts at the center, we also have the group of Jerry Gabriel's, where he's done precision measurement of the electromagnetic moment, as well as he's involved with obtaining limits on the electron-electric dipole moment and searching for fundamental symmetry breaking using anti-hydrogen. Also, Brian Odam's group is there. He does spectroscopy on trapped molecular ions and is looking at questions like, are the fundamental constants like mass, the ratios of mass of proton, for example, changing in time? We have a search underway for a fourth faculty member that's ongoing actually right now. Our lab is looking for fundamental physics using kind of an overarching theme of resonant sensors. And so in particular, I'm going to say something about our experiments using a very high quality mechanical resonator, which for us is an optically levitated particle. And I'll tell you about our efforts to use that sensor to look for new physics related to gravity. We also do experiments with a very high quality spin resonance, namely using NMR on laser-polarized gases. And I'll tell you about an experiment where we will look for new spin-dependent forces, in particular looking for this particle I mentioned earlier, the Axion. So in the first half of my talk, I will discuss an existing experiment where we're aiming at measuring gravity at micron scale distances using these optically trapped particles. And at the end, I'll tell you about some of our developing efforts to look for axions and other dark matter. Okay, so moving on to the physics motivation. On the gravity side, if you were to look, for example, at the relative size of the standard model forces for two protons inside of a nucleus, you see there's a huge discrepancy in the strengths of these forces, where the gravitational interaction between them is about 36 orders of magnitude smaller than the electromagnetic repulsion. And so this has led theorists to a problem that's called the hierarchy problem, which is namely trying to explain why gravity is so much weaker than the other standard model forces in nature, or cast in another way, between the energy scale of quantum gravity, which is expected to be at something like 10 to the 19 GeV, and the electroweak energy scale, which is at the TeV range. There's really no known physics in between there. So this leads to a big fine-tuning problem in the standard model, where in order to explain the mass of the Higgs that we've observed, one has to insert a parameter in the Lagrangian and tune it at the 32nd decimal point in order to make that theory make sense. And so one of the most well-known suggested solutions to this problem is supersymmetry, which, as I mentioned, is being looked for at the LHC. There have been other ideas put forward, for example, that there could be large extra dimensions in space that are sort of at the sub-millimeter size. And in these theories, then, this apparent really high energy scale is not fundamental, but rather it's just a result of a dilution as gravity propagates into extra dimensions in space. The point being that either one of these experimentally can produce a signal where the gravitational force between objects will change below some characteristic length scale, which for the theories I'll discuss tends to be at the sort of sub-millimeter level. And then the question is, then, can we measure this in a precision experiment in the lab? So if I look at the Newtonian potential between two masses, where I have the product of the masses divided by the separation distance times the Newton constant, then these new beyond the standard model physics effects would produce a correction to this of this Yukawa type form, where I have this term here in the parentheses. And so here I have two parameters here. So alpha is just a dimensionless number relative to 1, which is telling you the strength of the new interaction relative to the gravitational strength. And then lambda is the length scale, which basically is set by the Compton wavelength of the particle that's being exchanged. And so either these models of supersymmetry or string theory or the ideas of large extra dimensions can sort of naturally give you predictions in that sort of sub-millimeter range for these kind of effects. But let's look at the landscape for corrections of this kind over a larger range of distances to begin with here. So this, I'm plotting the same formula here for the Newtonian potential between the masses. And now I'm plotting the length scale lambda here all the way from planetary scales at 10 to the 15 meters down to laboratory scales here at 1/10 of a micron, 10 to the minus 7 meters. And the area here in yellow has been what's explored by experiment. And so any deviations above this yellow band here have been ruled out. And so by far, our best experimental evidence for this 1/r potential comes from precision lunar laser ranging experiments, which are at Earth-Moon kind of distances, where we know that there is no correction term here, where alpha would be better than about a part in 10 billion or so. However, if you look now on the left end of the plot at laboratory scales, you'll see that one could actually reverse the exponent here, and that at a length scale of a tenth of a micron, you could have an interaction here that's 10 billion times stronger than gravity, and yet there'd be no experimental evidence which would otherwise conflict with that. And so the reason it's difficult to put bounds on these potentials at short distances has to do, on one hand, due to the scaling of the gravitational force. So for example, if I just look at the gravitational force between two spheres of radius r, and I bring them as close together as possible at a distance 2r, I can write down the Newtonian force between them due to gravity. So I plug in the fact that the mass is due to some finite density and size, and then I realize that the force is actually going like the positive fourth power of the size scale. So if I shrink the system down, then this force gets weak very, very rapidly. And so taking objects that are as dense as I can find on Earth, on the order of, say, 20 grams per cubic centimeter, if I'm looking at the range of experimental interest, which is sort of at the 10, say, micron scale to pick a number, the force I need to detect here is at the level of 10 to the minus 21 newtons, which the prefix in SI is Zeptonewton. This is a very small force, and for those of us here who are not in the business of force sensing, I just want to give a point of scale. So imagine that if I had a person standing on a bathroom scale on Earth, they might exert a force of around, say, a few hundred newtons. If your bathroom scale was very precise, you might be able to tell the difference between, say, 700 and 700.1 newtons. However, if I wanted to detect the extra force if a single dust mite were to come and land on that person's shoulder, I would need a sensitivity of about 10 to the minus 7 newtons, or for a single bacteria, 10 to the minus 15, or a virus, 10 to the minus 19, or an extra individual carbon atom, I would have to be able to measure 10 to the minus 25 newtons. So the force I'm trying to detect is something like the force of the weight of a virus standing on your shoulder and then divided by 100. In terms of other more practical force sensors in the condensed matter physics, I mean, for example, the AFM is typically measuring forces that are around 10 to the minus 11 newtons, and so we're about 10 orders of magnitude below what an AFM is typically looking at. So this is only one of the problems that one encounters when trying to do these experiments. Another challenge has to do with the background forces. So while the gravitational force is shrinking and getting weak when I bring things close together because there's less mass contributing, the electromagnetic background forces are getting stronger. And so in particular, we worry about background effects, for example, from the Casimir effect. If I have parallel conducting plates, even with no electrical potential difference between them, there's a macroscopic attractive force between them that's just due to quantum vacuum fluctuations. That force scales like 1 over the 4th power of the separation distance of the plates and tends to get very strong at short distance, can easily swamp the gravitational signals we're looking at by many orders of magnitude. In addition, we typically use metal materials for high mass density and so forth. And on the surface of metal, even though what you learn in Jackson is that metals are equipotentials and have a constant potential everywhere, for real materials, for example, like gold, there can be local variations in the work function over the surface of the material where you can get local differences in the electrical potential on the order of, say, tens of millivolts. And those can also produce electromagnetic background signals in the experiments, which can, in principle, dominate over the gravitational signals you're trying to find. So now I want to zoom in on that same parameter space, but now looking at sort of the shorter distance end of the spectrum, where now my length scale lambda here is going from 100 microns on the right end all the way down to 10 nanometers on the left side. And my alpha parameter here for my strength relative to gravity is at 1 times gravitational strength at the bottom, all the way up to 10 to the 15 times gravitational strength to the top. The area in the yellow shaded region is what's been ruled of experiment as of current date. The best limits at kind of tens of microns of length scale come from precision torsion balance experiments that are done at the University of Washington, where they have a high sensitivity pendulum that's attracted to an attractor mass, and then the torsional oscillation of this is observed as it's connected to a torsional fiber. The best limits at the 10 micron length scale come from microcantilever experiments that were done at Stanford you have a cantilever beam with a test mass attached to the end, and you have another driving mass that's brought nearby, and the gravitational interaction between those masses is studied. At the even shorter length scales, the best limits come from adaptations of experiments designed to look for the Casimir effect, and they produce the best found in this area here. Some of the theory I mentioned earlier is predicting that we'll discover new things in these shaded regions here, depending on which particular model we're looking at. But so all of these sensors rely on some kind of mechanical detection, whether it's a torsion fiber or a torsion oscillator or a cantilever beam. And so I want to ask, what can we do to improve the sensitivity of these kind of mechanical sensors? And so let's look at just one example of which of these sensors, which is the cantilever beam. So the cantilever is basically like a mass spring system. You can think about it like a diving board. I apply a force to the end of the diving board, and I get some displacement proportional to the spring constant. So I can take advantage of the fact that there's a natural resonance in the system. And if I apply my force F at some specific frequency corresponding to the natural resonance, then I'll get an enhancement of the amplitude of the oscillation on that resonance frequency, where the amplitude I get is enhanced on resonance by the mechanical Q factor or quality factor of the oscillation, which is like an inverse measure of the dissipation in the system. And so for cantilever sensors like this mechanical quality factor can be quite large, can be 100,000 or 10 to the 6, 10 to the 7, even higher depending on the system. And so this is a nice way of taking a very small force and turning it into a very large displacement to sort of amplify the effect and be able to measure the effect of tiny forces. And so you can ask with this kind of approach, then what is setting the fundamental limit in terms of how small of a signal you can see? And so that turns out to be limited by thermal Brownian motion. And so you can think about that in an analogy with a particle moving around in a fluid. So if I have a piece of dust that's bouncing around a fluid, getting kicked around by fluid molecules, it undergoes some random jitter in its motion. Similarly, I have this cantilever beam that's in some finite, it's in contact with a thermal bath at some finite temperature. And so I can write down from the equipartition theorem in statistical mechanics that in the presence of these kicks from the thermal bath, there's a sort of minimum force I can detect on top of the presence of those thermal kicks. And that minimum force basically goes like the thermal energy kT times my spring constant times the measurement bandwidth divided by the product of the frequency of the oscillator and that mechanical quality factor Q all to the 1/2 power. So let's put in some numbers for silicon cantilevers like those used in the gravitational measurement experiment I mentioned earlier. So this is a silicon cantilever beam. It has a width of about 50 microns, a length of 250 microns, and it's only 1/3 of a micron thick, so it's quite floppy. It has a pretty small spring constant as a result. So this, put in a cryogenic system at 4K with a Q of about 10 to the 5, gives you a sensitivity that's about 10 times 10 to the minus 18 newtons per root hertz. And so you can ask, well, what can we do to improve this? So one thing we can potentially do is to try to improve the value of that mechanical quality factor to take some dissipation out of the system. And so in this kind of a sensor, there's a number of things that are causing some mechanical dissipation here. So first off, this cantilever beam is clamped to some substrate, and there can be energy flow into the substrate as the cantilever oscillates. It can also have surface imperfections over the surface that are dissipated as the device moves, as well as more fundamentally internally, there can be thermoelastic dissipation where the cantilever beam can move and energy can get lost in the process there as well. And so as a way of avoiding those limitations, then one can imagine optically suspending the force sensor, where I basically want to replace this cantilever beam with a particle that's trapped using a container essentially made out of light. And so I can take a dielectric object. In this case, we'll be using a nanosphere. This dielectric object is a polarizable medium, and so in the electric field of the laser, it acquires some dipole moment. And then I can use that dipole moment to create an optical trap where there is a potential such that the optical potential is deepest where the square of the electric field is the largest, or in other words, where the intensity of the light is the largest. And so I can create a trap for a polarizable dielectric particle where I have a laser beam focused down at a point. And now I can observe the motion of the particle in this optical potential, where now the restoring force of the spring is given by the gradient in the intensity of the light, as opposed to in this system where it's given by the mechanical flexing of the beam. So what I've done here now is, by looking at the center of mass motion of this object, I'm now very well decoupled from the environment. I don't have this thing mechanically clamped to any substrate, and as long as the device is, as long as the sphere is rigid enough, I don't need to be concerned with the internal materials loss of the bead itself. I'm only looking at the center mass displacement.
But I'm missing what's giving the sort of amplification that previously you were getting from the Q factor.
Yeah, so the Q factor in this beam is limited, as was mentioned, from the materials.
No, I understand why, but in your...
Yeah, so here, that's right. So here we can imagine working in a regime where the Q factor is going to be limited by the collisions of the particle with the background gas. And so if I remove the background gas, I can actually get a very high mechanical Q factor, and that's exactly the point, actually, of using the levitated...
My question is more naive.
Okay.
What's making a Q factor at all?
Yeah,
it looks like it's just sitting there in a potential that wants to sit in the bottom.
There are a few things, but the thing that we're the thing that we're most concerned with is collisions with the background gas, right? So you have this particle that's held up with light, and there are still gas molecules around at some level that will bump into it and damage it.
I think Gladys is asking about the curvature of the well, which is set by the strength of the focus.
Or another way to pose the question is, I could kind of guess over there. So I'm familiar with the torsion balance stuff.
Yes.
So I could kind of guess how the or maybe I even knew how the cantilever you'll measure a gravitational force, but I can't quite guess.
Yeah. So you have what you have here is an optical trap. So
Yeah.
you have the particle wanting to sit at the bottom of the well, like you said,
Right.
and it's the gradient in the intensity that's setting the spring constant. So there's a mechanical spring effect. The particle moves away from the bottom of the well. There's a restoring force from the optical radiation pressure that wants to push it back to the center, and that's proportional to the gradient in the intensity of the light. So here, if I apply a force to this object, it will displace from the minimum of its potential, and you can measure the displacement. There's a spring constant, and then from that spring constant, you can infer what the force is. So it's rather than looking at the deflection of the tip of a diving board, you're looking at how is the particle displaced away from the center of its potential.
I think what was confusing me is it seems like the displacement, which you have to measure, is actually smaller because you're forcing it to go up the hill.
Well, it's a question of the relative parameters of the systems, right? Yeah. So there's some stiffness and so forth. But as I'll show momentarily, the force sensitivity of this system can be quite superior to the other.
And you have a question. So the vibrations of the mirrors themselves, they won't introduce some effective destruction?
No, they can, of course, yeah. So the particle is still subject to environmental noise of various kinds. But there's no fundamental intrinsic limitation from the material itself in the same way that there is here. I mean, I can take this system and shake it around too, and it will affect the signal too. It's a good question. So now let's go back to our force sensitivity equation, but now for the levitated particle held up with a container from the laser light. And this is the same equation I had on the previous view graph. I've just rewritten it in terms of the mass of the trapped particle and the damping coefficient. Here I'm assuming the damping coefficient is due to the collisions with the background gas. And I've plotted here the minimum detectable force as a function of the particle size for particles of size at a micron and below, or a little bit above a micron. And so for a regime where I'm limited by the background gas collisions and my pressure is a respectable ultra-high vacuum environment at about 10 to the minus 10 torr, then even at room temperature, I'm able to sense forces that are at this 10 to the minus 21 newtons per hertz level or below in this kind of a system.
Sorry,
yeah.
Can you say how you measure the position of this particle?
I will. I'll get to that in a second if you don't mind. But yeah.
What's it a force between that you're going to measure?
Right. So for the experiment I'll describe, we'll be looking for these gravitational forces, and so you'll have the levitated particle is basically like a test mass, and you have another mass that will be the source.
So you have to have two levitated things.
Well, for our particular application, but anything that would apply a force to the system.
No, but I just wanted to know for your particular application how you were keeping the.
Yeah.
Essentially, you have to measure as you move them apart how the force changes.
Yes, and I will, if we can hold that just for a couple slides. I do have some pictures that might be easier to explain. So Okay, so, and already back in 2013, there was a nice demonstration of sensing at a level of 20 Zeptonewtons per root hertz using these kind of systems. The cantilever kind of solid state sensors I was mentioning earlier are showing sensitivities that are up in this range above 10⁻18. So there's several order of magnitude potential improvement by basically working in this high vacuum limit where we've removed a lot of the mechanical dissipation from the system. So if you look closely on the right side of the graph here, there is a little deviation from this line I've plotted from that equation. So this is actually due to a quantum mechanical effect that is known as photon recoil heating. There's basically scattering of the Rayleigh scattering of the trapped laser photons as discrete events can cause the particle to get kicked around and heated up to some extent. This was experimentally observed for the first time a couple of years ago in a slightly different system. But so the point is that you can stay pretty close to this pressure limited sensitivity even at 10⁻10 torr for a pretty wide range of particle sizes. And so the potential is quite good for sensing at this level. So using this system, then we're operating an experiment. Here's a cartoon version of the experiment where we have a nanoparticle that's a sub-wavelength in size, and it's trapped in an optical trap. In this case, we're actually trapping it in a standing wave optical trap. So we have a set of nodes and antinodes of the optical field along this axis of an optical cavity. We trap a particle in one of the antinodes of that optical cavity where it's attracted to the maximal intensity point. One of the mirrors of the optical cavity is a thin membrane that's made of silicon nitride and coated with gold. And then behind that mirror, I have a device which is basically the source mass in the experiment. It consists of material with alternating sections of gold and silicon. And so gold and silicon have a density contrast that's about 10:1. And so when this device with that density contrast is then mounted on an actuator which can move up and down in this direction. And when I do that, then I basically modulate the density that's closest to the trapped nanoparticle. And in doing so, I modulate the gravitational interaction between the two. And so I have this rigid conducting membrane in between the two to screen the electromagnetic and other kind of background forces here, where the gravitational signal is modulated behind the screen. It's not screened by this that membrane. So then using this system, we're estimating that it's possible to improve the limits on this Yukawa parameter space by several orders of magnitude at the 1 micron length scale. So the actual experimental setup looks a little more like this. So we have this optical cavity here along this axis. So I have my mirror here, and the driving mass device is behind this mirror. We have another set of lasers that we call the dipole beams. We use those to initially collect our particle. And then we have an additional set of lasers that we can use to do laser cooling in 3 dimensions on the particle, and I'll explain how that works in a moment. So here's a picture of our test mass. This is a 300 nanometer diameter piece of glass, silica glass, that we trap in this potential. The actual inside of a vacuum system looks like this. This is the axis where we have this optical cavity where the particle is trapped. Behind there I have an actuator which moves this mass structure, and then I have this perpendicular trap here that's formed with these dipole beams that I used to originally catch the particle and then eventually transfer it into that optical cavity trap. So the driving mass itself that we're using to source the gravitational force looks like this. It's made from a silicon wafer that we deposit gold into. So we etch trenches into the silicon wafer. And then this is 20 microns here for length scale. We electroplate gold into the trenches. And now we have this density contrast between the gold and silicon sections. You'll note, though, that when we do this, we see a little bit of corrugation on the top surface of the gold. So you can see a little bit of memory of this spatial period here in the top surface. And we don't really want that, because we don't want any electromagnetic signal to basically be modulated at the same spatial frequency as this density modulation is occurring. And so in order to avoid systematic background effects due to that, we basically take this device and then glue it onto a glass substrate and then turn it upside down, and we actually polish away the silicon wafer from the back side. And so here's a picture taken with a focused ion beam, and we've cut into the material in the middle of that process so you can see what's going on here. So we're polishing away the silicon wafer, removing the silicon, and we eventually stop when there's only 1 to 2 microns of remaining silicon above that those gold depositions there. And you see the surface here is then very flat and smooth, and then we can deposit a uniform conducting film on top of that surface and then have very little modulation in the electromagnetic forces. So this device is then positioned on a homemade MEMS actuator, where it's basically a capacitively driven cantilever beam, where basically we can capacitively excite this tip with an amplitude of a few microns that's sufficient to modulate the gravitational signal at the level that we need in the experiment. So, we catch the particle initially in a standing wave optical trap that's made with these dipole beams. So we have 2 beams that focus down to nearly the same point. They're offset by about 75 microns. So the beams here are primarily orthogonally polarized, so they don't interfere completely, but we do allow some of the same polarization to come from the opposite direction, which allows me to create kind of a shallow standing wave or optical lattice trap along this beam axis. So this is the force along the axis of the laser as a function of position, where this width here is due to that interference in between the two beams. And so you see here there's actually a corrugation in this potential where there are several positions along here where I can trap one of the particles in these in the antinodes of that standing wave. And so when I catch a particle in there, I can actually, by perturbing it with another laser, I can actually make it move from one of these trapping sites to another trapping site, which are basically set by half the wavelength of the laser. So in order to get the particle in the trap, it turns out to be a little bit tricky. So we load the trap basically by taking a substrate and depositing some of these nanoparticles in the substrate and then just shaking it very, very hard. And it turns out that that becomes a non-trivial problem because due to the van der Waals interaction between the nanospheres and the substrate, there's a scaling where the acceleration you need to basically knock this thing off is going like 1 over the square of the radius of the particle. And for the size nanospheres that we're using, at 300 nanometers diameter, it turns out you need about 10 to the 7 Gs of acceleration to knock off that thing. And in fact, we've measured that in the lab, and it turns out that that's really what it takes. If you go much higher than that, then we start breaking our piezo ceramic disc and so forth. And so this is kind of close to the limit, I think, of what you can do with this technique, but nevertheless, it does work for the sizes that we're using. Here's a little movie I wanted to show you, kind of just to get the feel of what it looks like when we launch and catch these things in our traps. So this is an earlier quartz enclosure that we did some experiments on. What you're seeing here, we have 2 counterpropagating beams. They're scattering off of the walls of a container. They come to a focus there somewhere in the middle. On the left side here, I have a smearing of these particles where I'm going to shake the substrate, and the particle is going to fall down where gravity is actually pointing to the right here, so this picture is tipped sideways. So you're going to see the particles fall, and then you'll see them get collected in the trap. So here particles are coming down under gravity. Here we catch one in the center where the beams overlap. In this case, we caught a couple of different particles, and they kind of came into some rotational state. And so we tend to operate in the limit where we only have 1 particle in the trap at a time, ideally. So if you look at this movie, the movie is actually done in real time. And so we've shaken this thing that's not slowed down at all. So you can really see these particles are falling at a pretty slow rate. And we need to do that on purpose because we need there to be some damping or dissipation in the system in order for the particle to get caught at the bottom of the trap and not just fly through it as if it were ballistically flying, in a vacuum. And so we actually need to have a certain amount of gas in here to damp the motion of the particle, whereas to do the experiment with the very good sensitivity, I need to get rid of the gas to be really in the ultra-high vacuum limit. So our group and several other groups were noticing that we were having a lot of problems keeping the particle in the trap when you first start off with this kind of medium pressure all the way down to the high vacuum limit. And so we think that this, one of the reasons for this had to do with some instabilities that we discovered, which we've since attributed to radiometric forces. So I'll just tell you a little about the story for that. So this is a glass container which is mostly evacuated, which is now a toy you can buy at a museum store. But back in the 1800s, it was a state-of-the-art experiment done by Crookes, where he had thought he had discovered the force due to radiation pressure. And so here we have this partially evacuated bulb. You have these vanes here which can spin, and one side of the vane is bright and highly reflective. The other side is dark and very absorbing. And so if radiation pressure was what was pushing this thing around, you'd actually expect it to spin the opposite direction, because the momentum of the photon getting reversed from the reflective side would cause it to push harder basically on the reflective side. In fact, it looks like it's pushing harder on the dark side. And the reason for that is that the dark absorbing surface is getting heated up by the laser, and the gas that's around that dark surface then picks up kinetic energy from bouncing off the hot surface, and you can create a current of gas which actually drives the thing in the opposite direction. So the radiometric force from that gas current can actually dominate over the radiation pressure force. And it turns out that in these traps there are similar effects going on, where now we have a laser beam that has some finite waste and size, and you can have an intensity gradient over the surface of our particle, where some part of the trap particle is hotter than another part. This can cause the particle to get kicked out of the trap, and it tends to be most important when the mean free path of the gas is basically of order the object size. So you can calculate the expected value of that radiometric or photothermal force as a function of the pressure. And so just focus on the black curve here. So there's some range of pressure ranging from around, say, 10 torr down to about 10 millitorr, where this radiometric force is staying very constant, while at the same time, if you start off at a higher pressure here and you start to pump out the background gas, your gas damping coefficient is dropping, while this radiometric heating force is staying constant. The result of that is that your center mass temperature is actually increasing as you're removing your gas damping, until you get to the point where the heating rate is actually overcoming the gas damping rate, and the particle gets kicked out. And so as a way to circumvent that, you need to reintroduce damping into the system. And the way we do that is using laser feedback cooling. So we have the particle trapped in our optical potential, and then we image the scattered light from the particle onto a segmented photodetector. And that gives me a three-dimensional, if I have a couple of these detectors, I can get three-dimensional position information of how the particle is moving. Then I can take that position information and phase shift it to get the instantaneous velocity of the particle. And given the instantaneous velocity, then I can feed back to another set of lasers where I have control in 3 dimensions, where I can basically create a velocity-dependent damping force which can slow down the motion of the particle and then stabilize it in this regime where these radiometric forces are acting. Now you may worry that I tried to sell this story by saying there's no damping in the system, that's why this is such a great sensor, and now I've thrown the damping back in the system, and how is that going to be useful? And so it turns out that if you look at this formula for the minimum technical force, it goes like the square root of the temperature over this mechanical quality factor. And so while I am reintroducing the damping here with the laser, I'm also decreasing the temperature by essentially the same factor. And so it turns out that I'm preserving the ratio of the temperature over this mechanical quality factor. So I get to keep the same sensitivity that I would have had even in the really, really high mechanical quality factor limit. So once I apply this feedback, I can bring the particle down to high vacuum. And then once I'm at high vacuum, I can actually decrease the feedback quite substantially and still keep the particle around. So that really showed that the gas was responsible for that instability. But in that regime, then once I'm at high vacuum, I can now do very high precision force sensing. So here's some data showing integrated force sensing down at the level of 6 Zeptonewtons, or 6 times 10 to the minus 21 newtons, where I've integrated down here for, in this case, 10 to the 5 seconds for my averaging time. So my sensitivity is about 1 attonewton per hertz in this particular experiment. This is limited by technical laser intensity noise, and so at this pressure, we think we can get about a factor of 10 or so, better than that even. And so, so this shows then that this system can achieve force sensing, which is really interesting for the gravitational experiments. However, so since we're in the business of looking for hypothetical new forces which may or may not be there, we would like to convince ourselves that if the force really was there, we would have we'd really actually be able to see it. And so it's useful to calibrate the system by applying some known force to make sure you can actually see a force as small as you infer. And so we do that a couple different ways, one of which we can do an electrostatic calibration. So it turns out that most of these particles are collected with no net electrical charge, and they tend to stay that way. Once in a while, we get a particle that has, about 10% of the time, has either 1 or 2 extra electrons on it. So inside of our cavity, we have a set of electrodes where I can apply a known voltage, and then I know the electric field at the location of the particle, and from that I can calculate the force on it for either 1 or 2 electrons. I can use that as a way to benchmark and make sure that my force sensing is actually at the level of where I think it is. For those particles which are not electrically charged, it's also possible to do a calibration of some kind. We do that using this optical trap itself. So I mentioned earlier, I can make the particle move from one trapping position to the next trapping position by kicking it. And so I know the spacing between these positions is a half wavelength of the light. In our case, that's 532 nanometers. And so then I can use that spacing basically as a ruler to calibrate the position spectral density of the particle. And from that, I can infer the force in that way, knowing the spring constant. The method that we have here is consistent with the measurements for using the electric field on the charged particles.
So what was B inverse?
This is the inverse bandwidth, if you will. This is in units of seconds. Yeah, so this is like the averaging time of the experiment.
So 10 to the 5 seconds is like a day, right?
Yeah, a couple days. Yeah.
How do you have so many data points? I mean, does it take that long to collect this?
Well, so it's running continuously for a couple days, and you're averaging the force down. And so if the system, this is dropping like the square root of the averaging time essentially, which means that I'm limited by a noise process that has that particular scaling. Like for example, the thermal noise. In this case, we have some technical laser noise. But so if there was a background problem with like mirrors vibrating or some other vibrations which are above that, this would level off. You wouldn't be able to keep measuring down indefinitely. And eventually, if you probably continued this down, you'd start to see it turn up at some point. But so at least up to this level, it's still dropping in the sense that we can average that long and continue to gain sensitivity, at the level where we're in this 10⁻21 regime.
Okay, so this band is an average that takes several days. It's not a bunch of discrete data points that each take several days.
Correct. This is a single data run
Yeah.
that was undertaken for that long. That's right.
And you haven't seen a noise floor yet? You stopped at a day? Cause
a couple days, yeah. I mean, there are sometimes when you, if we had somebody kick the table or something, you'd see effectively. But yeah, generally speaking, we don't see much at that time for several experiments. Yeah. Okay, so given that we have the sensitivity, then we are now working on doing the gravitational measurement in the cavity. And so we can take the particle and transfer it to the optical cavity trap, where I have 2 different colors of light in the cavity, one of which traps the particle, and the other one can both read out its position along the axis of the cavity and cool it along that axis. And so here's a photo of the particle now trapped in the cavity. These are the calibration electrodes. We have temporarily been interrupted by our recent lab move, since we just moved 3 months ago. So we're in the process of reassembling the system and hoping very soon to get back to continuing on this, and hopefully in the next year or so have some preliminary results for sensing near the surface. But so in the remaining bit of time, I wanted to say a little bit about some other potential applications for these levitated particles that have demonstrated this good sensitivity, one of which could be using them for gravitational wave detection. So we've recently discovered that gravitational waves can actually reach the Earth, and we can detect the strain from space-time in the LIGO interferometers. And so it's possible to think about these levitated particles as another way of doing gravitational wave detection, but now on the higher frequency end of the spectrum. And so the idea is you have an optical cavity, kind of like the one I showed, except now it's much longer. We're considering a length that's on the order of, say, 10 or 100 meters. And you have a particle trapped in an antinode of the field inside the cavity. If a gravitational wave comes along, it can put some strain and change the physical distance between the mirrors of the cavity. And what that does is change the location of the standing wave antinode relative to where the particle is sitting. And so that can put a force on the particle, which can cause it to oscillate and basically ring up in that optical potential. So you can kind of think about it like an optical version of the old style gravitational wave detectors, which are these giant bar detectors, as they're called. So here's a picture of Joe Weber in the 60s with an aluminum bar detector, which basically rings like a bell. If a gravitational wave of the right frequency comes along, it excites this thing up into some resonant oscillation, and you can observe that. Here we have the mechanics spring constant coming from the optical field, and so I can tune the laser intensity basically to adjust the resonant frequency of the optical trap and then scan over a range to look for signals from the passing gravitational wave. And so if you had a 100-meter cavity, you can get strain sensitivities at the level of 10 minus 22 per square root of hertz at high frequency, which can then exceed the sensitivity of things like advanced LIGO in the high frequency band. And so what we've essentially done here, you can think about this as sort of turning LIGO's position measurement problem into a force measurement problem, where at high frequency, LIGO is limited by photon shot noise in their ability to measure the distance between mirrors. Here, we're limited by the thermal Brownian motion of the particle in the trap. And those two things actually have a different frequency scaling. And so by essentially turning the position measurement into a force measurement, we actually gain sensitivity at the high frequency end, whereas the LIGO detectors are tending to get worse. So here's a plot of the strain sensitivity as a function of frequency from 10 to the 4 kilohertz and up. And so you can see the LIGO sensitivity is tending to get worse, while as for these levitated particles, it's possible to actually improve it. The one caveat is that at these high frequencies, there aren't so many conventional astrophysical sources of gravitational waves. So if you had primordial black holes that were sort of solar mass size, you might expect to see signals as high as 30 kilohertz, or possibly higher harmonics from things like mergers and things like that. But I think an interesting thing to look at here was actually related to beyond the standard model physics. In particular, is a process known as black hole superradiance, which Sergey is actually one of the co-authors on some of these ideas, where you can have clouds forming around black holes within our galaxy, which would produce clouds of QCD Axions, which can annihilate into gravitons and produce a kind of monochromatic long-lived source of gravitational waves in the frequency band of, say, around 100 kilohertz. Another point, though, I think, is that we've only recently discovered gravitational waves, and it's interesting to look, further into the spectrum than over the range we've just been exploring so far. And so to experimentally test this, we're developing experiments that are now based on fiber-based cavities, where we can ideally get a relatively inexpensive setup, assuming we can keep the noise under control, where basically we trap a particle in sort of a small free space cavity and then have a 100-meter long fiber with a reflector on the end that basically creates my 100-meter baseline. And so we're investigating how simple this is to actually get to work in the lab now. So in the last 10-ish minutes, I wanted to at least mention something about our other experiments, which are related to the dark matter. And so there's a fair amount of evidence that dark matter is out there. There's no uncontested evidence from either colliders or large detectors for what it is. And so one possible particle that may constitute dark matter is known as the axion. So axions are quite generic theoretically, and the axion was invented by Pecci and Quinn to solve a puzzle in high energy physics known as the strong CP problem. Or in other words, in order to explain why the neutron has such a small electric dipole moment. So there's an angle parameter in the QCD Lagrangian that would naively be order 1. And if the axion exists, then one has a dynamical mechanism which can drive its value quite small to be compatible with the measurements which have now put a bound that this angle theta QCD has to be less than about 10 to the minus 10. So the Axion also, in addition to solving that problem, is a very good dark matter candidate because its mass and abundance and interactions and so forth that can naturally explain dark matter. And so there are experiments which are searching for the Axion as dark matter. The ADMX experiment, I showed a picture of it in my second view graph, is a microwave cavity experiment, for example, looking for Axions converting into photons. We're doing an experiment. We're also looking for Axions, but in a slightly different way, where the Axion is now, for us, going to be a force carrier that can mediate spin-dependent forces between objects when you bring them together at close distance. And in this way, we can source the Axion locally in the lab, as opposed to trying to interact directly with the dark matter field if the Axion is, in fact, dark matter. So our experiment is called ARIADNE. It's a collaboration between us as well as people at Perimeter, Stanford, Indiana University, and the Center for Axion and Precision Physics in Korea. So the Axion is a nice particle to search for an experimentalist because it's characterized in terms of a single parameter, which is its mass. So here's a plot of the allowed parameter space for the QCD Axion in terms of the mass of the Axion, going in electron volts here on the horizontal axis. So the blue shaded areas are what has been ruled out according to astrophysics. And so we know the QCD Axion must have a mass that's lighter than about 10 to the minus 2 electron volts due to astrophysical constraints, for example, from supernovas or white dwarf cooling and so forth. The Axion mass may also be bounded on the lower end depending on cosmology. So if you have a high energy scale of inflation, there'd be too much dark matter if the Axion were lighter than about 10 to the minus 6 or so electron volts. But of course, depending on the model of cosmology, it's possible the Axion mass could be lighter. So the Axion mass can basically be anywhere between about 10 to the minus 2 electron volts down to below nano electron volts. The ADMX experiment I showed before is looking over a pretty narrow part of the allowed parameter space. Their second generation that's under development is planning to cover a wider part of that unexplored area. There are bounds on heavier Axions from experiments like the Axion Solar Telescope CAST and then its proposed upgrade, which is called YAXO. And there are other experiments that are being constructed which will be able to look for lighter mass. But there's a lot of space here that's not yet explored. And our experiment, ARIADNE, is trying to basically close in this gap here where no one's really looked for Axions between sort of 10 millielectron volts down to 100 microelectron volts. So ARIADNE is a little different than other Axion experiments in the following way. So if you characterize these experiments, you can sort of make a table in terms of the source of the Axion and what the coupling is. So the Axion couples to photons in addition to nucleons in most models. And so the ADMX experiment, as well as several proposed and developing extensions of it, are looking for dark matter Axions coupling to photons. The CERN Axion telescope is looking for Axions from the sun. Our experiment is basically looking for Axions produced in the lab as they are a virtual particle exchange between matter. And so we're looking for the coupling of Axions to nucleons. So Axions can produce forces in the following way. So there's generically a scalar coupling, which one might expect to be related to theta QCD, and a pseudo-scalar coupling, which basically looks in the non-relativistic limit like the gradient of the Axion divided by the Axion scale, semi-pitchy twin scale FA, dotted into sigma, which is the spin of the fermion. And so if I have two nucleons, for example, I have a vertex here, I can either have an interaction between the nucleons with the Axion acting as the force mediator, where the vertices here could either have two copies of the scalar coupling, what I call the monopole term. I could have one monopole term and one of the dipole term, or I could have two of the dipole terms. And so our experiment is looking for interactions of this middle kind, where I have a product of the scalar coupling and the pseudoscalar coupling. And so if I have a mass and a spin, there's an interaction between the mass of one fermion and the spin of another. And so I can write down a potential due to this axion exchange, which basically goes like sigma dot r. So sigma is the spin of the fermion, and r is the distance from that to a nearby mass. It goes like, it's exponentially suppressed here, where lambda a is the Compton wavelength of the axion. So the mass of the axion is basically setting the range over which this force exists. I have a 1 over r squared term, and then I have, again, this product of the coupling constants. And so because it couples to the spin sigma of the fermion, which is proportional to the magnetic moment of the fermion, we can think about this like as an effective or fictitious magnetic field that's present due to this axion potential. But it's very distinct from regular magnetic fields. It doesn't obey Maxwell's equations. And important for our experiment, it's not screened by magnetic shielding. So it's possible to use magnetic shielding to block regular magnetic field noise, where this new axion-induced potential would be able to penetrate through the shielding. The mass of the axion, the constraint we have from astrophysics, where it's less than a few millielectron volts, gives me a target here to look for with this length scale, where we know the lambda, the interaction range should be something like 30 microns or larger. So one way of looking for this is to do an experiment based on NMR. And so, for example, if I take a spin 1/2 nucleus like helium-3, and I put it in an external field, then I have an energy splitting between the spin up and spin down states of the spin that's set by the nuclear Larmor precession frequency. For some reason, there's an H bar missing over here. I'm not sure what happened to that. So, but the idea is then I have some external field, and the helium-3 nucleus is sitting in that field. If I bring a mass nearby, then I feel this additional field. This is this fictitious magnetic field, and that can then modify this nuclear Larmor precession frequency. And one can look for a modification in that Larmor frequency when you bring a mass nearby the spin. And there were several experiments that were done looking for this kind of effect. So this is a plot showing the product of those two coupling constants, the scalar and the dipole coupling, as a function of either the force range on the bottom, this is from 30 microns up to about 10 centimeters, or in terms of the QCD axion mass, this is the heavier mass axion at a few millielectron volts down to microelectron volts. And so these precision magnetometry experiments have excluded everything above this blue shaded band here. It was pointed out that if you combine astrophysical results with experimental results, you can exclude a more aggressive part of the parameter space here that's in the shaded tan area. But if you were to ask where do we expect the signal to be from the QCD axion, it's actually in this purple area here, which is several orders of magnitude below where we've probed. So there's a band here that has a thickness to it. The upper part of the band is set from our limit on the neutron electrodipole moment. We know theta QCD is less than about 10 to the minus 10, so that's setting the highest value of this coupling. But also there's a lower bound here on the coupling, and that's because there's a certain amount of CP violation that's already present in the standard model, and through higher order effects we get theta QCD that we expect to be bigger than about 10 to the minus 16. So there's this 6 order of magnitude range here where one would naturally expect the axion to be if it were to exist. So the ARIADNE experiment is also an NMR-based experiment, but it's using a resonant technique where we can enhance the signal in the following way. So you have, again, a helium-3 nucleus, which is spin 1/2. You put it in an external field, and you have this energy splitting here, which is set by that nuclear Larmor frequency. And we bring a mass nearby. But now the idea is to oscillate the position of the mass physically in space. And when I do that, I'm basically I'm modulating the strength of that fictitious magnetic field. And this field is basically transverse to the applied external field. And so this is basically using NMR where I'm driving spin precession in the helium nucleus by modulating the fictitious field from the axion potential. And so I'm doing this on resonance. This allows me to get an enhancement due to the again, a quality factor in the system, where the quality factor is actually due to the product of the frequency omega times T2, which is the transverse decoherence time. So then this spin will then process. It requires some transverse magnetization, which one can detect with a magnetometer, in our case using a squid magnetometer. So the actual experiment looks more like this, where we have a sample of polarized helium-3 gas in an enclosure, and then I have a unpolarized mass that's a tungsten cylinder with some teeth in it. It looks kind of like a big gear. So the tungsten cylinder is rotating, and as the teeth of the gear pass by, then we cause the spin to precess around its axis, and then we can pick up that precessing spin using a squid magnetometer. And we need to have a magnetic shield between the two so that we can screen ordinary magnetic field noise and so forth. And so this helium is actually enclosed in a piece of glass that's coated with niobium superconducting thin film as a superconducting shield to block the magnetic noise.
So like in Casper, you don't care if it's dark matter or not?
We do not care if it's dark matter, that's right. Yeah, since we're generating the signal itself, right? So the limit comes from quantum projection noise in the spins themselves. Here's a photo of the design of the main probe. So we have this spinning tungsten rotor here, source mass with three detectors, three helium-3 sample chambers. Looking down at the top here, there's this is 4 millimeters for scale. There's about 50 microns between the surfaces of this rotating mass and the edge of the sample chamber. We have the helium in a flattened kind of pancake type geometry here, and the mass is spinning around in this direction. This is in a quartz block that's coated with niobium. So we have 11 segments in this wheel, and our target frequency for the nuclear spin is 100 hertz. So that means we're actually physically spinning the wheel at only about 9 hertz to decouple things like mechanical vibration. Our helium density is of order 10 to the 21 per cubic centimeter. The volume of the sample is about 1 centimeter by a few millimeters by 150 microns, with an average separation of a couple hundred microns. And so our projected sensitivity on that same plot is shown here. So depending on what T2 we can get, whether it's from 1 second up to, say, 1,000 seconds, we can basically exclude everything above this red band. And so then this allows us, in principle, to start exploring into the actual predicted parameter space for the QCD Axion, where again the win here is due to this resonant enhancement technique. And so assuming we have all the systematics under control and so forth, one could imagine scaling up the system to eventually carve out some part of the parameter space here with the solid blue line. If you ask what is the limit from the magnetometer of the squid that's detecting the spins, then that's actually all the way down here, which would be sufficient to basically rule out the entire thing. And so I'm running out of time, so I'm going to go ahead and wrap up shortly. We have several noise sources and systematic effects we worry about in this system. It's not by any means an easy experiment. We're doing some work now to characterize things like the magnetic gradients and vibrations and background magnetic noise from impurities and so forth. And I'm going to go ahead and move a little quickly here towards the conclusion. So we've started building and testing the superconducting shielding and made a prototype of our source mass. We've been happy with the level of residual magnetization that we've measured, and we think it's going to be adequate for the experiment. We've tested our rotation mechanism in the experiment, which also looks quite quiet. So let me just go ahead and conclude. So I've talked about a few different methods that are based on AMO physics that are looking at sort of high energy physics things at the sensitivity frontier. So first off, we've shown that you can do calibrated force sensing at the level of 10⁻21 newtons with these optically-levitated particles, which is about an order of magnitude better than any solid state room temperature force sensor to date. And we're excited to get the system put back together to continue our investigation of these gravitational effects at short distance. In the future also, maybe we're interested in exploring whether we can actually get the mechanical mode of these devices into the quantum limit. And there's some interesting applications that may come up there that I didn't have time to mention. And then ARIADNE is a new experiment based on NMR, where we're aiming to close this gap that currently exists in the search for the QCD Axion. It's really complementary to the other existing experiments, and since we source the axion locally, it doesn't depend on the dark matter density, and also we don't need to scan any mass or field or anything. We basically explore all the masses that are contributing to the distance range between our objects. And we have another effort that we're developing, searching for light dark matter using interferometers, so I didn't have time mention. And so with that, I just wanted to thank our funding and show the people actually doing the work, and thank everyone here for your attention.
So in the first experiment, you described this source mass, or whatever you call it, this gold and silicon that you shake. Do you have a problem with Casimir or Van der Waals or something, just because there's gold that's closer to the nanoparticle and then further away closer?
Yeah, so there's sort of two levels of screening against the Casimir effect that we need. So one of which is, so there's a membrane between the drive mass device and the sensor. That's just a flat silicon nitride coated with gold. So that's completely uniform over the surface. It doesn't have any corrugation associated with the pattern in the drive mass device itself. The drive mass device itself, as I mentioned, we had that elaborate polishing process where we had to basically turn it upside down and get rid of the silicon. So there we are worried about any corrugations in the electromagnetic signals that would occur at the period of interest, but we can get the material flat enough with a uniform enough film that we don't see any evidence, at least, of electromagnetic effects. And we had a similar technique we employed in the Stanford experiment with cantilevers, and it was sufficient for that, and so we expect it to be good enough for this too.
Actually, I have somewhat exotic question for particle theorists to ask. But so this amazing force sensitivity which you have, are there other applications of it, more like down to earth?
Yeah. So one could imagine different kinds of sensing. So inertial sensing, accelerometry, and that sort of thing would be one thing you could do for practical devices. If you had some way of functionalizing it, either with charge or magnetic properties, you could imagine maybe doing, magnetic sensing or electric field sensing or something like that.
So you show the force sensitivity, which was limited by gas collisions.
In the theoretical plot?
In the theoretical plot, this,
yes.
This black and red curve. So
yes.
So suppose you were to pull a better vacuum and you were truly limited by the 0-point motion of your sensor. How far down is that?
Yeah. So I don't know if I can find that curve quickly, but I had a little bit of a quantum effect shown on that graph, which is going to come in before you start to see for things like, say, standard quantum limit from the measurement of the particle. So hold on, where is my thing? Getting close. Yeah. So over here, there's a limit that deviates from the gas. That's at 10 to the minus 10 torr from that's this photon recoil heating, as it's called. So that would be the next thing I think that would show up. If I were to bring this down, then you'd start to see that curve come in.
Before the 0-point noise.
That's right. Yeah.
And so gamma in that formula there that's the
rate. This is from the gas.
Yeah,
damping.
That's the rate of collisions with the gas molecule.
Correct.
No questions. Let's thank Andy again.